Hello. So in this video we're going to be looking at indirect proofs. This is just an introduction to the mechanics of indirect proofs, a lot of which can be applied to conditional proofs as well. This video assumes that you know the rules of inference and the rules of replacement pretty well, that you can do the proofs, some fairly good, complicated proofs in those chapters, and that you're ready for the next stage. So I'm not going to spend a lot of time looking at the details of how to do how to manipulate rules. We're going to look strictly at the new things with the indirect proofs here. So the big difference between the indirect proofs and what we did before, which we can just call direct proofs, is that in a direct proof, as you know, you go use the rules and you go step by step, seeing which new step follows necessarily from the previous ones until you get to the conclusion. And when you get to the conclusion, you're done. So it moves directly from the premises to the conclusion, building each step up, and so you know each step or each new premise that you have is necessarily true. With an indirect proof and a conditional proof, we are going to be making assumptions within the argument. It's kind of like building a sandbox within the world of the argument that you can play around in and see, like, suppose you were just pretend that something else is true. Suppose you were to just assume that K is true. What can you figure out from that? And sometimes it's just a matter of learning the argument, but with the indirect and conditional proofs, it ends up being a very important part of the argument. The reason why we use indirect and conditional proofs is that sometimes it proves to be impossible to get to the conclusion only using the rules. There's no direct path in some cases. And in other cases, using a conditional or indirect proof doesn't make the impossible possible, but it does make a very, very long proof into something simpler. Having said that, the most challenging proofs that we've encountered so far can be done, will often be found at the higher levels of using indirect and conditional proofs. So let's talk about how to set this up. So first of all, in an indirect proof, you can assume whatever you want to. The way you show that you're making an assumption is you leave a space right there, which you don't actually draw. You leave a space, then you draw a vertical line, and this is like a barrier that says we are now in assumption land. And in assumption land, you can assume whatever you want to, but there's some things that are more useful than others. If you are planning on using the indirect proof, then you will assume the opposite of a statement you are trying to prove. And for a lot of the first problems, for a lot of the beginning problems, the opposite of what you're trying to prove is simply the conclusion. But you can just as well assume the opposite of a statement that is elsewhere in the argument, or that you need elsewhere in the argument. So if this is a very long and complicated proof with 20, 30 steps, it might be step 15, like maybe you're on step 7, you understand that there's something you're trying to get to, that you need this, and you're guessing, you don't know where, but you know it's down the road somewhere. You don't know how to prove it, so instead you assume the opposite. And that's not even the conclusion, it's just somewhere in the middle of the argument. So that's a valid way of using this. But these earlier problems don't make us do that. You can always just start by assuming the opposite of the conclusion. Okay, so once you've put this there, you've put the opposite of the statement you're trying to prove, and then instead of writing a rule, you're going to write AIP, which stands for an assumption for an indirect proof. And likewise, if we were doing a conditional proof, you would write ACP. And you'll assume something different for those, but we'll save that for a later video. Okay, now here's the thing. You know premise 1 and premise 2 are true. You're assuming not n is true. But if you assume not n is true, you wouldn't be able to put not n over here, because that would be declaring it's true. But you could take these statements and put them over here. And the reason why that's true is something like this. If you know these statements are true in the baseline argument, in the argument with which we're working in, then they'll still be true in your hypothetical. It's kind of like, I don't know, it's kind of like watching a television show that takes place in New York City, where the characters in the show are not characters you're going to find if you actually went to New York City. So New York City itself, the real New York City, is like the baseline argument. The things that are true in the real New York City are true, are like the things that are true in this argument. But suppose, I've been watching the show Seinfeld lately, and the characters and the situations that appear in the show, they're imaginary. They're not actually real. I mean, they're kind of based on real people, but they're not actual people or situations you're going to meet. I mean, there's the character Jerry and there's the real life Jerry, but they're not actually people you're going to meet in the city. However, the city is something you'll meet in the show. You will see things like Central Park or whatever existed at the time when the show was out. So that's kind of like here, where you can always see the real city in the land of assumptions, but you're not going to find the made-up stuff or the assumed stuff in the regular argument, unless we can prove that it's there. Okay, I don't know if that analogy was helpful. I'm going to pretend that it is and move on. So we assume that not n is true. Now at this stage, we can manipulate the not n just as if it were a regular argument. So if not n is true, and if this is true, then you can see modus tollens is a legitimate step, and you could write not r or m. And that is from 2, 3 modus tollens. Okay. And you can keep doing that, building the assumption, and so long as you are sitting within the realm of assumptions, you can keep going. So now we can do De Morgan's. We can say not R and not M. And that's from 4 De Morgan's. Pretty cool, huh? All right. Now, like I said before, and now the example is a little bit clearer, what I cannot do right now, I could not simplify step 5 and put it there, because then I'm ejecting or I'm leaving or I'm dismissing the assumption. But the only reason I was able to get to not R was because of the assumption. So this right now is based on an assumption, whereas the only stuff that should be here needs to be established as something sure, not as an assumption, or not something that's derived from an assumption. But we can keep doing it down here. All right. Now let's take a moment, because now you kind of get what it is that we can do, what it is, how to function in this, but what are we aiming at? This is what we're aiming at. If we know that these are true, and we're being told that the n follows necessarily from the premises, then you might have wondered, why are we assuming the opposite of the conclusion? Obviously, if this argument is valid, then not n cannot possibly be true. It's the opposite of what should follow. Why would we assume not just what we don't know is true, but that we know cannot be true if the argument is valid? Why are we assuming what can't be true to prove that the argument is valid? Well, this is what we're aiming at. What we're trying to do is to say this: if not n is true, then there's going to be some contradiction, that it's ultimately going to lead to something like this, a statement that shows a true and a false of the same statement, which cannot happen. We're saying P is true and P is not true. And within our realm of logic, that's not possible. If we can show that not n leads to an impossibility, then we know that not n must be false and that the assumption was wrong. And then we'll know something about not s. We will have gone from no knowledge of an assumption, or from a mere assumption, to actually knowing something about it, even within the realm of the assumption itself. So as we say not r, then I can use, I better be good, and write 5, simplification. And then I can use not r with modus tollens on line 1 and get this. So that's from 1, 6, modus tollens. Then I will use implication, not k or k, from 7, implication. Then 9, I will use De Morgan's. And look at this. Now I am saying that k is both true and it is false, which cannot possibly happen. And if we found out that this, which follows from this, which follows from this, and so on, all the way up to this, if this is our only assumption, and it led us to what is impossible, then we know that not n cannot possibly be true. And if not n is necessarily false, then the opposite of not n, which is n, is necessarily true. So once we have found a contradiction, you can eject yourself from the assumption, take whatever it is that you assumed, put its opposite down on this line, and now you have proven that the n is true from the indirect proof. If that didn't make sense, I would go back and listen to it again. But if we started with an assumption, we found that it leads to a contradiction, then you take the first line of your assumption and put its opposite down here. Okay. Now, one other thing I need to say, well, two of the things I need to say. Once you have this, then the proper way to label this is you write from lines 3 through 9, indirect proof, since we went through all of these steps to get to the n. All of them combined, not just 3 and not just 9, but all of them combined. Another thing I need to say, one last thing I'm going to say, is that you cannot put in a second assumption within this argument. You have one assumption and that's all you get. We will learn about something called a nested proof later, and what that's going to look like, well, what that's going to look like, suppose we had this, not n, and if we wanted to make a second assumption, what you got to do is make a second assumption over here, not p, or something like this. And this can go on technically an infinite number of levels of the assumption, and you got to move out of them one at a time. It kind of gets very Inception-like. So anyway, that's the basic of the indirect proof. Many of our first arguments, until we get into the more complicated stuff, most of our first arguments will not require those nested proofs. It'll just require something like this, and that's it. Thanks for watching. If you have any questions, bring them to class, or leave them in the comments since I'm putting a video on YouTube. Hope this was helpful. Talk to you later.